All right, always interesting to see the turnout on the final day of the Skyjam. Who wants that last little bit, and who's like, okay, I don't need any more. So welcome. And today, actually, a lot of people, we believe it or not, we do read the feedback you give us before you come to the course, and a lot of people were interested in PRM. So I thought, the people who were dedicated enough to show up on Friday morning we're going to do a little PRM session because there's not really anything PRM specific on the schedule, but hopefully anybody now could have some idea of how to set up PRM based on what we've learned with SRM and DIA and stuff. But anyway, we're going to go ahead and do it here in the Skyjam. And so go ahead, and if you don't have your flash drive plugged in, plug it in, or if you've already copied all the files, you can just wait while I copy the files that I need. So in tutorials, I'm just going to grab what we used to call PRM, targeted MSMS. So there's a folder called targeted MSMS, and if you don't already have it on your computer, just grab it and drag it to your documents folder. And these are pretty tiny little data sets. Also, you can certainly do much larger PRM studies than these. These are just teaching examples. As yesterday was the calibration, we calibrated one peptide. I'll point out that there's a webinar on calibration, and if you do that, it will point you to Panorama and Panorama Public. There's a great data set full of calibrations, and that is we flipped everything around from what I'm used to seeing. So it's really the first public data set in Panorama was this large-scale interlaboratory study from CPTAC. So if you wanted to do more, if you wanted to play around with Skyline's calibration more and actually do something with lots of peptides, that's a great place to go. Okay, so back to if everybody's files have copied, then inside this documents folder is the targeted MSMS folder, and there's low res and TOF. Even the TOF data is kind of old now. But this is with an LTQ, and so it is possible to do PRM with low resolution instruments. You don't need a Q exactive or anything. So this is Agilent data, and here you can see it's a calibration curve on BSA, and there's actually a document in here. So I guess actually I could close this. So yeah, we're not gonna create the document today. We'll just double click and open the BSA Agilent document. You can see it's pretty small. There's a set of peptides. They all already have library spectra associated with them. And let's see, looks like top 6 ions have been chosen for all the peptides. But there are no precursors. So let's go to settings, transition settings. And yeah, you can see top 6 are picked here. If we go to the full scan tab, you can see it's not set up. It's currently set up for SRM. There's nothing set up in the full scan tab, so we're going to go over setup for PRM. You probably yesterday already did some setup of MS1 filtering for your DIA data. We now default to centroided. I'm going to switch this back to TOF because I've never tried it with centroided. And then the resolving power, I said this is kind of old data. The resolving power is 10. We'll use 10,000. And then with still, I've been thinking about changing this, but still the synonym for PRM in this UI is to say you want targeted acquisition method. And then now we default to a sort of high resolution TOF, and we're gonna put that back to 10,000. We don't need high selectivity extraction because this is not a very complex sample. And I guess it's really. Oh, okay. So we're just gonna include all matching scans here, and this is what Jarrett told you was not the greatest thing to do, and you can read here that it says full gradient. So with DIA, this is definitely not a great thing to do. PRM, again, works more like SRM, and so usually you would have scheduled before or not, and so like your extraction for PRM is usually less important than because you should have set up your extraction before. Let's see. And then now we're going to switch back to filter, and you can see that we have 2, 3, 1, and as I mentioned, there's no precursor ions yet, so we're going to go ahead and specify that we want precursor ions by just putting a P at the end there. So this is a sort of good set of steps. If you had a document that was set up for SRM and you wanted to switch it to PRM, this is what you would probably do. And then click OK. And so now you can see we have gotten 3 precursors. We've got the M+1, M+2, and the precursor. We're going to have 3 isotopes just like you had for DIA yesterday. And then we're still going to have our 6 library transitions extracted. And so, oh, I get it. Yeah, okay. So we're going to go File, Import, and we're going to import just one replicate to start. We're going to import our most intense replicate, and this is actually going to get to what was being asked recently about, can I import one replicate and use it to schedule everything else, or can I use it to restrict retention time? So that's what we're going to do here. We're going to go ahead and do we're just going to import one replicate, so okay, and we're going to import the most intense replicate, which is number 6, and open it, and it should extract pretty quickly. So let's see. So let's arrange our windows a little bit. In small experiments like this, I usually just dock the retention times and peak areas over on the right side. I'm going to take the library and I'll just dock it with peak areas. I'm not going to be looking at it very much. And maybe give a little bit more area to peak areas since we're splitting. So, yeah, we can look at each one of these peptides. What the I.Ps, does everybody understand I.P at this point? Right, so I.P is the isotope dot product, and they're really high. In general, you should be looking for much higher I.Ps than library.ps, although the library.ps are pretty good here, but they're consistently lower, right? They're 0.86, 0.93, and the I.ps are very close to 1. Same thing with R.ps. Do people understand what an R.p is? You've done labeling, so it's the ratio. It's how well the heavy and light pairs match. So those also should be really high, and if they're not high, it's an indication of interference. So yeah, not all .p's are the same. What are some reasons that .p might be lower? Right, like so there's actually quality in the .p. It's a library, right? So what are some reasons that your library might not match your measured results? Yeah, you got a public library, in this library, right? So you have no idea where it came from, right? It might have come off an LTQ, and you're measuring on a Silex Q-trap, right? So that's that. So you should have in your mind, what is this when you're thinking about .p's, you should have in your mind what is the source of my library. And I have actually seen Skyline uses the dot product to pick the peaks, and I've seen people who've used libraries that are so far off what they're measuring that Skyline will start picking just really wild peaks, and they go, why did Skyline pick this little thing in the dirt here? And it's like, well, it's because your dot P is 0.3, you know. So you have to have some. You should always be thinking when you get a new library and you're going to try to use it. Be thinking about how high you can expect this. Whereas I.P, where does it come from? Like where do we get the idea of what we're comparing against? So there's an expected for I.P. For both of these, we've got an expected distribution and then the real distribution. And where does the I.P distribution come from? Yeah, it's like we calculate it. So like there's not the source is always the same. It's always elemental composition, just in silico calculated. It really should be this, and it turns out that we're really good at that calculation, and usually we get very high I.Ps when the data is good. So it's definitely a good measure of your current data quality, while .p again depends on a prior measurement, and depending on how good that prior measurement was, your .p's are going to differ. So we talked a little bit about chromatogram libraries that could be stored in Panorama. Those would be really high quality, right? Because they're based on prior measurements with the same instrument and the same setup and everything. So we would expect the .p's to be higher. And how about R.p's? Why would we expect those to be pretty good? Yeah, we've got a standard saying that's behaving the same as the standard, and by definition it's measured on the same mass spectrometer, So yeah, okay. So let's see. So we have really nice quality. If I'm zoomed in, if you're not zoomed in, if you are zoomed in, then press Shift F11, and now we zoom out and we can see what kind of a gradient was this. Well, we have 30 minutes, so I don't know whether that means, does that mean we have a 30-minute gradient or a 45-minute gradient? Anyway, so we measured in the mass spectrometer for 30 minutes. So we have 30 minutes of time in the mass spectrometer, and we've just picked this peak, and it turns out that, in this, I'm going to go edit, collapse all peptides. In this case, we have beautiful peaks for everything. But now we also know where to find these things, right? So now we can go back and we go to our settings, peptide settings, and go to prediction. And then you want to make sure that you want to make sure that the prediction is based on that you have this checkbox checked. Use measured retention time on credit. So that tells Skyline that I'm allowed to predict where something's going to be based on data that I already have imported. And so then that should be fine. Just click OK. It's already set on mine, if but make sure everybody has it set. And then now we go to transition settings, full scan, and now we can say use scans within minutes of predicted RT. So click that, and we're going to change it to just one. So we're going to say, yeah, we think that we did a series of measurements, and we think that all the other measurements are going to appear within a 2-minute window, centered around our prior measurement. Yeah.
The semi of yours were both of yours that the time defined is both ways.
Yeah, it's a plus or minus. It's a plus or minus. So I try to be as quick. This says within. And in Skyline, if you ever see the term tolerance, that means it's a plus or minus value, and if you see window, that means it's a one big thing centered around. So yeah, so if this said use a window, then it would be you'd have to write 2 nines, right? So that's so let's click OK here with our 1 minute tolerance plus or minus value. And so, yeah, I think sadly, this is a little confusing. In peptide settings, we're using a window, right? So it's not a plus or minus, it's 2 minutes around the thing. But we're not using that value, we're overriding that value with the transition setting. So this is if we were to go out and schedule new PRM, we would end up using this. If we exported a scheduled method right now, we could have a 2-minute window, or we could say, oh, actually I want to schedule with a 3-minute window or whatever. But extraction happens based on the transition settings. So I'm going to cancel that. Okay, so now I think we're ready to import the rest of the data. We can go File, Import, Results. Whoa, what's it doing? Hide that. File, Import, Results. So now it tells me it says, okay, well, you have some imported data. I'm surprised that I actually showed this, but I have one. It says you have some more imported data. It's double checking. Okay, you want to predict based on the prior imported data, and you can choose a single replicate to schedule on, or if there were multiple here, you can check them all. But yeah, we realize that frequently what people will want is, because you might have retention time drift, you might want to choose the last one only, or you might want to choose them all you might want to choose them all and average them or something. But anyway, so in this case, just check that one and say okay. Yeah?
Did we take the highest signal here just because we're sure that we have all the peptides?
Yeah. We happen to know that, that this is really good data, and so we're going to look for everything based on what we saw with the really good data. So that's why we picked it. Yeah, if we picked the lowest concentration, we might have nothing, right? We might have already hit the lower limit of detection, and we'll see in a second whether we can actually see anything on that lowest level. So click OK to just allow Skyline to schedule, again, single injection replicates, and click OK again. And so now we just select everything but the big one. All the other 5, you can select them by dragging out a box like I did, or click and shift click, but select them all and click open. And my window is gone. Yeah, well, they're going to come in pretty quickly. I don't need to see the pretty graph. Okay, so let me pull out. I'm going to grab peak areas and pull it out so that I can see it bigger on this monitor. Wow, things drop off pretty quickly. let's go ahead and switch to log scale. So maybe how about order required time? Well, let's go, yes. Go back to order document. Let's reorder the replicates. Edit, manage results. Everybody have it imported? Okay, so go to manage results and let's put our, everything in order 1, 2, 3, 4, 5, 6. Do you have a question?
This last process of the asked you this question about
Yeah.
this only works in PRM, but doesn't work in right?
No, it works. That works in anything as long as you've got the use measured results. As long as you've imported some results and you say use measured results, and then your prediction is based on your measured results. So Skyline is going like, okay, I'm going to use measured results like you told me. Which set of measured results do you want? So you have to have things set up to use the measured results. But then, yeah, Skyline will always ask you, oh, okay, which measured results? Okay, so click OK. So there we go. So just looking at this, whoa, can't do that. We've found that zooming doesn't work very well. But so, does anybody see anything noteworthy at this point? Yeah, what's going on with 50 animal? Why is it high? Why is it higher than even 1 femtomole and even 10 femtomole? Right? Mislabeled. Well, let's see. So, and let's also see what happens when we do order by acquired time. Nothing changes. So not only was it mislabeled, what order do you want to measure a calibration curve in? Lowest to highest. So we may have created carryover effects for ourselves by measuring this high one before the lower ones. But yeah, so really, if we went edit, manage results, and move 50 attomole, and assume that actually what was meant was 50 femtomole. Oh, I'm still in acquired time order. So order by document, and now it looks a little bit better. But you may also feel like, well, that's not very linear. But you have to remember that this probably is 50 femtomole, but it was the first thing you measured. So everything else is sort of benefiting from potentially some carryover, right? And this one isn't. So that may be why it's not so linear. Should we do people? Any questions? Any thoughts? People want to set up a calibration curve? Check the linearity of this. So yeah, so that was pretty simple. We could go, if people want, we can go do the low res example. But that was mostly what I planned to cover today on PRM this morning. We could look at the data. We could look at actually chromatograms. Yeah. Okay. Interesting.
If you look at the block peak area.
Mm-hmm. Oh, that one kind of goes down, huh?
Did we get misled by this force peptide?
I don't know. I think really it is probably the difference in this carryover effect. Like you have to remember that it's not measured as a. Oh, that's kind of cool. You have to scroll through it. You just select the top one and you can see the peak rate of one. So I mean, you can see they all dip a little bit. There's not, so, but it is. But you're right. It's more pronounced on 2 than on the other 3. I think, yeah. I think we just really couldn't use this calibration curve. We should go back and rerun it with everything correctly labeled and everything correctly ordered. Yeah. Oh, so let's go. I'm gonna put this back. And let's go view arrange graphs tiled, so we can see everything. Not really a whole lot of room to see everything. I'm gonna make my targets view smaller and my other view smaller. And then now, well, let's look at only, let's not do split graph. Let's go transitions products. So now we're looking at the product icons. And you can see that I'm zoomed out, right? So that, but you can see that that this is the only one that has 30 minutes of chromatic now, right? These guys have 2 minutes of chromatic now, just like we set it up to do. And yeah, the chromatography. We can look at the chromatography here, and you can see that the chromatography is quite stable. So that was safe to do. So that can definitely help Skyline a lot in terms of peak picking as we get down to the lower intensities. At the very lowest intensity, it's possible that Skyline might have found something else that was better in the entire chromatogram, or that looks better in the entire chromatogram, and go out and. But it's limited to 2 minutes. Questions? Okay, what do you want to do next? You want to break, or do you want to go and look at the low res PRM as well, which is kind of interesting. Opinions? What? Yeah.
Essentially record all your strokes, so you can go back and check if you find something that isn't behaving properly, and possibly even be able to send it to you as a bug report.
No. There's no stroke recording, but there are annotations, right? If you find something interesting, you can annotate it. So we can go to settings, peptide. We can go to document settings, and we can go to add, and we can add a non-linear annotation and make it a true-false annotation, and make it apply to peptides, right? So define annotation, nonlinear, true, false. You can come up with all your own annotations and add them to the document. And now we go here, whoops, right? And there's these 2 peptides, this one, and I can now right click on it. Whoa, didn't quite like that. I can right click on it and edit note. And then I can say, yeah, this was at one of the nonlinear ones, and so was this last one. Edit note, nonlinear. Okay, so now if I hover over this little triangle, I've got nonlinear true, nonlinear true. So I have annotations, and you can definitely send us documents. We love that, and that would just be, we would just go file share. Complete, and share it. That's fine with Skyline Zip. And now you can send this to us, or you could put it up on your panorama project and point us there, and say, hey, what's up with these 2 nonlinear peptides? And we'll take a look. Yeah. This has to be integration. And we'll go, yeah. You no, actually I know because we'll open it up and go order by acquired time and go, hey, wait a second. you you oh, actually I noticed something. Oh no, that's there. Okay. So I thought for a second there maybe, like, you can see how poor this lowest 100 animal must be, because there's really no signal from uh, anything. There's only signal from two transitions, and actually here it is. You can have a look at the chromatograms that this is. So you may be. So I mean, this is kind of interesting. When you get down to the really lowest levels, you sometimes start to lose anything that can be interpreted as coevolution. So although this is, it seems to be a collection of signal from the things we're interested in, so maybe we want to expand to grabbing all the signal, but it's not. It doesn't look like coevolution. Again, you can see the little. I'm sure you played with this yesterday. You can see the little circle, so you could click on that and have a look. And actually, I'm not even sure this is profile data now. This may have been pre-centrated data. I think it was actually looking at a higher. Yeah, so this is pre-centroided data, and you can see the full isotope distribution for the y-ion. Because there's only a stick here. There's not a, there's not a. This is the empty dimension, and there's not a distribution here and lines going over the top. Yeah. So because it's pre-centrated data, I would say now we could go back. Let's try that. So we went, whoa, it's centrated data. Let's go back and see if we get better results if we go to settings, transition settings, and instead of saying it's TOF, we say centroided. And I'm going to say I bet it needs at least 20 ppm mass accuracy, and then I would do centroided and 20 ppm mass accuracy. And then okay. Now what I'm really not sure about is, can I just go here and I'm not sure this is going to work at all, but can I go here and select all of these? So manage results, edit manage results. So if everybody has changed their settings, do people catch that? Do people follow along and change their settings? Yep. Okay. So then you can go to manage results, select everything, and click re-import. Get a little asterisk by all the things, and then click OK. And here you can see it's happening. It's not. And I'm unsure. Yep. Did it work? Yeah. Okay. So that then should have imported as now using a centroid extraction. We would expect this extraction to look narrower than it looked before, because 20 ppm. There we go. 20 ppm is quite a bit narrower than 10,000 resolving power. So those resolving power numbers translate into how wide these windows are. And so 10 ppm, that's the 10 ppm extraction window. Or 20, yeah, we did 10, plus or minus 10. No, did we do 20? Yeah, we did 20 ppm extraction window. So, yes, things still look pretty good. Anybody want to try 10 ppm extraction window? Okay. Well, wonder, do we have enough time to?
You can be the workflow for PRM if you have the data from proteome discovery.
If you have the data from proteome discovery. Oh yeah, so one of the points that actually actually I don't have. Well, let's go see the low res example. So go ahead and save your. You can close them full scan window and redock the peak areas and save. So in the low res example, we actually have a peptide search here. So it's a peptide search in the format that the MacLean lab does theirs. It's like SQT files and PerkXML. It's a pretty old peptide search, and then MS2 files for the spectra. The interesting realization I made with PRM after working with it a little bit was like, oh, it's essentially it's not very different from DDA data. You're going to have a lot of scans that are going to be basically garbage because they're scans over where you're not really expecting to find anything, but they're all centered with a narrow window around the precursor. And so my thinking was, well, normal search tools should be able to find the things that were when you see a chromatogram coming up, a normal search tool should be able to identify that as what you're looking for. It's an isolated, it's an MS-MS spectrum from an isolated precursor. It's just that we've chosen which precursors to isolate rather than letting DDA randomly choose them. And the reason I thought it was kind of important to have some garbage spectra is that that's just the case in DDA. You're going to have some garbage spectra. We don't expect our tools to match every spectrum, and so if you threw out a search tool something that was only really great spectra, I'm not sure how well the statistics in the search tools would work because they sort of expect these two distributions. There's definitely like peptide profit sort of expects to have two distributions. It expects to have this bimodal distribution, and if you actually manage to filter out enough of the really bad stuff, then peptide profit I think gets confused. Okay, so that's what we have here. Let's go ahead and click new. Or do we click new? I'm not even quite sure. Or do we have a I think we have a starting project. So click File Open. I wasn't expecting to get to this, so I didn't really print out. But yeah, so here's an existing BSA. This is the label-free method. Again, it's another BSA digest. So click it, open it. This is what the researcher chose to measure. Actually, I think this is the BSA, bovine albumin, and then they also measured two peptides that were somehow mixed in, or two peptides from two different proteins, modified and unmodified. So they were studying phosphorylation. This is from a paper, one of the original papers on what we called at that point pseudo SRM. And so you can see there are a lot of fragment ions getting extracted, which again is fine. They're not like transitions. You can extract as many as you want. So let's go to settings, transition settings, and look at so again, we have no full scan set up. This is all low resolution data, so we're going to go with count QIT and just a single peak. And in the MS filtering targeted, and it just selects QIT for us. And we'll just go include all matching scans. Everybody have that set up? Okay, and then since we're extracting MS1, we would like to be able to have precursors again. So switch back to P, or switch back to filter and add P. And click OK. And now we have the sad realization that these peptides are already edited. Somebody has gone through and chosen transitions manually. So if you hover over the precursor now, like this 5823190, and click on it, you can see, oh, this is really old data. So normally it would have, it wouldn't be in this state. This is sort of showing that it's picked. Yeah, this is a weird state it's in. But anyway, so I guess we're going to go ahead and click choose that precursor itself. And then that's where Skyline then shows you this little wizard wand with a red X through it, meaning like, okay, this was chosen by a person, we better not mess with it. So that sort of fixes the transition choice. And then what I'm going to suggest for this is that we'll just go through each one of them and manually add the precursor. Another option, what would be another option to sort of change this document to get precursors added? So we've realized that, oh, there's a bunch of manual editing here that's keeping us from getting our precursors. What's another option to get the precursors into the document? We'll try that in a second. Anybody have an idea? What? From refine, yes, exactly. So we'll take a look at that. So everybody remember edit refine, where we set things like, we want a minimum of 3 transitions and, maximum of, okay, so I've done all of mine. And that shows up in the undo list with a whole bunch of pick transitions. But let's also go and see what happens. Let's keep that. We can go edit, refine, advanced, and now we can tell it to just auto pick all transitions. So this will just wipe out all those little red circles with the wizard wand. I'll just wipe them all out. So if you've done any manual editing, it's like, nope, just go back to my settings. So click OK. And this would be the default set. And so the ones with libraries, we would pick the top 6 or top 6 fragment transitions. But then we get down here and we have ones that don't have libraries, and so we're picking a lot more. And I'm going to click undo. Just go with what the researcher who had this project did, and you can see that she's already picked transitions that she thinks work pretty well for the ones that don't have libraries. So we're going to take advantage of that rather than just extracting all transitions. Okay, so we've got the document set up, and now what we want to do is we want to get our peptide search in at the same time as we import our data. So Control S to save this, and then File, Import, Peptide Search. And I guess I'm gonna, well, it's probably fine. So we'll use a 0.99 cutoff, which in this case, because we use percolator, would be a Q value cutoff. So that's basically saying 1% FDR. And we're going to go ahead and add files. So we're going to treat this as DDA with MS1 filtering. Can we do that? I think so. Add files. And then we go to the search. And in the search, we want to pick only the perk.xml file. So click and then hold down the control key and click again to pick the perk.xml and not the SQT files. And click open. So here we could, including ambiguous matches is fine here. I don't think there will be any, but we could also choose to tell it that we really don't care about any matches other than our document peptides, which is true in this case. And we don't have any IRT standards. So next. And then Skyline looks at those perk.xml files and builds a library. Matt Brace is hard at work on the Dropbox. Okay, so now then Skyline just automatically says, oh, well, I've noticed that your searches were against these two files. So is that what you want me to extract from? And you say, and that's yes. So we just go next. And we can go ahead and remove this prefix on these very long file names. And we've already set up everything. Maybe we don't want to change extraction. I don't know. Do people want a 5-minute window on extraction or a 5-minute tolerance on extraction, plus or minus, or do you want just include all scans? Skyline will do pretty well either way, I think. Include all scans so we can see the full chromatograms that are there if they are there. And then finish. The red is just to tell you, hey, if you just include all scans, that could make things bigger and slower, and so it might. And so it's kind of just a warning for in general. A lot of what we do, we don't want to use include all scans. We were kind of fooling this, and it doesn't really know that we're doing PRM at this point. So in PRM, it's more appropriate to include all scans if you've done scheduling. But yeah, in DIA, like Jarrett was just like banging his head, going like, this totally doesn't work. And I finally like looked at what he was doing. I'm like, oh, you're just including all scans always. Like, of course, Skyline's not going to pick great peaks in DIA if you include all scans. So yeah, and it leads to really huge files because that include all scans means we get a chromatogram for every chromatogram is across the entire gradient. So the files can be like 10 times as big. Okay, so close. We did get some extraction. Seems to have worked pretty well. I'm going to get back out of log scale here. Right click on my peak areas. Turn off log scale. The .p's look pretty good. I'm going to arrange my windows. Take the library, put it here. You're free to arrange your windows however you like. But yeah, so now you can see, here's down at the bottom, these are some of the more interesting ones. You can see cases where we have that's pretty cool. Yeah, you can see where the search engine has identified spectra, and let's pull this out here. quite understand that. So then you can see when I choose a precursor, now in the library match view, I get a drop down, and you can see just how many spectra were identified, and at what times and which files. And then you can either change this, so you can put the focus in this toolbar here, and then now you can go through and see just how well the spectra over time match, right? And they match pretty well. It's pretty cool. But you can also see that out along the edges we get a lot of noise, and so we have to change Skyline's spectrum picking algorithm, because it was originally based on how well each spectrum matched every other spectrum, and that meant that Skyline would favor really noisy spectra. So we would always end up picking something out on the edge here. And now you can see that the best spectrum, if I choose here, well, you gotta zoom in, but it does a pretty nice job of picking the spectrum right at the apex, right? So Skyline's gotten a lot better at that. In this case, it's picking an earlier spectrum. So it does a combination of the score that the spectrum gets and the intensity of the spectrum. Now, let's go ahead and say view arrange graphs tiled so that we can see both of our concentrations together. If you go back up to the top, and actually I'm going to edit collapse all peptides again, you'll see that, wow, with these spike-ins, we can detect them at just crazy times. Right? Like, wow, look, I can even zoom in and, they're just like really coming out at really, so they're injected at a very high concentration, even though I have this nice peak here in the middle, where they're quantitative for chromatographic quantification, they still show up at all kinds of weird times. And so this is, maybe gives you an idea of why also it's really hard to use these spectrum times for IRT, right? Once again, it's like, and I've definitely seen cases where maybe it just starts being detected here, and then the peak is tailing, and it gets detected all the way out here. So even trying to use median time, we end up like somewhere here, which is not representative of the apex. So it's a very, I think we do as well as anybody else, and maybe better after some recent work, but it's a without any visibility into the actual chromatograms, it's very difficult to come up with really accurate IRTs. So. Oh, and so then there's one other thing I like to show. Let's go ahead and right-click in the chromatogram graph and turn off the peptide IDs for a second. The chromatogram graph, turn off the peptide ID. So you right-click in the chromatogram graph and then peptide ID times. And is everybody showing both of these matching and aligned? From yesterday, I'm assuming that this got set up during DIA or something. I don't know, or maybe I've just got it set up. Did everybody have aligned? Yeah. Okay. So aligned means that. So what? Do people know what aligned means? Okay. So aligned means that the IDs in your other files are getting sort of transposed into your file. So you can see these light blue lines here. There's like the dark blue lines, and those are the actual IDs in the file. And then you see these light blue lines, which are aligned IDs. And we can, let's go take a look at view retention times alignment. And there's only one alignment. Wow, that's terrible alignment. Yeah, so it's based on a whole bunch of IDs that are in our library. I mean, I would say probably, yeah, this alignment is garbage. And if there's any sort of thing to align, it's maybe this line here. But it's an incredibly useful view to look at when you're doing this sort of thing. So the aligned ID times in these runs is garbage. Like it provides no value here. We're gonna look at an experiment starting in a bit when everybody gets here. I'll give you 5 minutes break where the alignment works much better. But yeah, whenever you're relying on this type of alignment, you should definitely double check it. So let's turn off the peptide ID times, both of them. And let's go back to transitions all again with split graph and arrange tabbed. And one of these has this really interesting effect. Huh. Maybe that's it. I don't know. Oh yeah, that is it. Huh. So this DRVY HPF, you can see that the MS1 chromatogram gets really overwhelmed by noise here, but the precursor, the product ion chromatograms, the fragment ions stay very clean and nice. And this is just an expression of why selectivity matters. I mean, so as we get to lower concentration, we can still, you can get a sense of why this might still be within the linear range for fragment ion quantification, but not really within the linear range for precursor ion quantification. All right, so 5-minute break, and then we'll come back and talk about MS1.